Yes, set. So hi everyone. Very glad to have this chance to share our recent work with professors and friends. And also I want to thank the department for giving me the 6-year support. All the works are done in the past year. It's important. I'm advocating for the 6-year support for the PhD program.
Thank him first. Thanks the organizer first.
Oh yes. Thanks the organizer of the probability and statistics seminar, and thanks the department. Yes, so today I'll talk about a new approach for the callback strategic insider equilibrium problem. So this is a joint work with my advisor, Professor Jianfeng Zhang, and the mass finance postdoc Weixuan Xia. So there are 4 parts of this talk. First, I will introduce what is callback model and review some classical results and trying to point out what we want to improve. And then we'll propose our new approach for the callback model. And then since the callback model typically doesn't have unique equilibriums, we propose to study the set value of it. And lastly, we use our approach to study a more practical phenomena observed in economics called stealth trading, which basically means that when there is a prosecutor inside, the inside trader will try to hide themselves while still making profit. Right. So what is a callback model? Basically, it's a classical economic model that describes the price impact when there is an inside trader present in the market. So it's a market of one asset with value V, and insider is the only one who knows the asset value. And based on the asset value, insider will determine how much she wants to buy or sell. We denote as theta. So noise trader is not strategic at all, which is modeled by a Gaussian process. Gaussian random variable. So this is first a one-step model, which is a simple version of the callback model, but contains all the important features to help build some understanding of this.
What do you mean by not strategic? There must be some particular meaning.
So noise traders are not trading to make a profit or anything. There is no goal for a noise trader. They are just present.
Noise traders are not trying to make a profit?
Well, at least in this setting, we're not assuming that they are doing so to make a profit. But it's important.
I think that it should be not making profit for the information. Everybody is trying to make a profit, of course.
Okay, that's fair. That's fair. Yeah, everybody is trying to make some money. Okay. But in this,
there must be some meaning of strategic, even for the insiders. Insider meaning insider being strategic means what? When you say very casually, they are not strategic. That means somebody is strategic, somebody is not.
In this model, I think that's how we want to model it. Insider make some strategic choice using their control theta, but and trying to make money through actually knowing the value V. But no trader doesn't.
We can discuss it later. You can move on.
Okay. Yes, looking forward to discuss it later. Yes, the market maker does not know the true value of V, but knows the prior distribution of V. He received the total order, which is the sum of the insider order and noise trader order. And
since it's internal seminars, I'll help you to answer. By strategic means he has a goal. He wants to maximize something. There's a goal. Non-strategic noise trader, there's no goal.
That's right. Noise trader doesn't have an objective in this model.
No.
Yeah.
Also, strategic probably means doing it legally.
Okay.
That idea.
Yes. At least not illegal in the inside trading way.
Like not using future information or anything.
Sure. Yeah.
This, although he knows the information, but the strategy is adapted.
I'm trying to understand.
Okay. Yes. But if they
Okay,
does not
anyway.
use it, then that's irrelevant. Right. So, oh yes, back to the market maker received the total order, which is the sum of the insider order and noise trader order, and then determine the market clearing price, which will further specify later. So now the problem for the insider is, so insider want to find for a given pricing rule P, insider want to find the theta star, a strategy that maximizes her profit. So the profit is organized in this way, calculated in this way. So the amount she buy times the difference between the true price and market clearing price, or the price set by market maker, and the conditional expectation because the insider knows the true value of B. So we denote this mapping from P to theta star as phi 1. And the market maker's problem for given strategy theta is to find the market clearing price P such that is close to the conditional expectation of V given Q. Yes.
A quick question regarding the noise trader C is independent of the V.
Yes.
Is there a good interpretation of this, and is this crucial for the model setup of the proof trader?
I think that's crucial for the definitely crucial for the model setup. So the noise trader basically is just well, it's like a background noise. So while they're just that amount of trading happened in the market, and then the V is just, the V random variable V is market maker's interpretation to the future value.
The noise trader is independent with all those information?
In the model setup, yes, but I guess you can make a point that they can be correlated, but I think that's not the objective of the model here.
Okay.
I think that will make some difference to the model. Yes, thanks for the question. Yes, we denote the market maker's problem as phi 2, but you can just take the market clearing price as a conditional expectation, and that's how previous literature typically phrase the model. So here we phrase it as an optimization problem just to emphasize the game structure here. So for the audience who are familiar with game, where in game people try to study a Nash equilibrium, which is a strategy pair that when your opponent doesn't deviate from the Nash equilibrium, you're better off not deviate as well. So that's a case in the for the insider problem in the callback model. So a callback equilibrium is when P using when the market maker using strategy P star, the insider should use theta star, and when insider use theta star, then the market clearing price should be P star. So it's like a fixed point problem in that way. Okay. Any more questions about the setup? Okay, so we'll actually solve it for the one-step model with slightly more conditions given. So suppose V is normal, and also importantly, we assume the model is linear. So the strategy insider strategy is linear function on V, and the pricing rule is linear function on Q. Here. So given pricing rule mu plus lambda Q, then the insider payoff is of this form. C is normal, so that disappear. We got a quadratic function on theta. Finding the theta that optimize. So we want to find find the theta that optimize this value. So we got a linear function on V here. So alpha star is 1 over 2 lambda, beta star is negative mu over 2 lambda. And next, for when the insider strategy is fixed, the pricing rule becomes the market maker's problem is to solve the conditional expectation of the Gaussian normal random variable. So we just plug in the formulas, and we can just since C and V are independent, so that we can easily solve this the covariance, for example, will only depend on alpha star and the variance of V itself, and variance of these two, sum of these two are the sum of their variance. So we got two equations, 1/2 lambda. This part are from here, just solving these equalities. So 1/2 lambda will equal to this huge part, and also 1 over lambda is also equal to beta times this huge part, which definitely tells us that beta is 0. So indeed, after solving it, we got the optimal strategy theta to be sigma over sigma 1 times V, and pricing root to be sigma over 2 sigma times Q. So we can look at this a bit more. So what does it actually tell us? So sigma is the variance of noise trader, and sigma 1 is the variance of the a priori distribution of V. So when noise trader has a large variance, in fact, insider can trade in a larger volume, so that he is more. It's like in a way, it's like a disguise. Hiding is a. They were able to hide in the noise trader. Okay, but this will be this kind of behavior will be discussed more in the first part. Another important thing to mention here is that so this linear assumption is important. When it's not linear, then we cannot there's no uniqueness result established even for the one-step callback model.
So the P star the quotient sigma over sigma 1 for theta and P star, theta star and P star, it's kind of reciprocal, right?
Yeah.
Which means the market price is higher, you trade lower, or what does that mean? Is that the interpretation? Sigma over sigma 1 will be small if the P star is big. Because it's a reciprocal, right?
Yes.
Which means P star is the market price. Theta star is the insider's strategy.
Well, it will also depend on the Brownian motion now. So the Q will be.
I just look at this quotient. If the sigma 1 over sigma is big, meaning the market price is high. Theta star will become small because it's reciprocal.
So not necessarily consider because so sigma will be the variance here of the noise trader as well. So and then the price will determine by this times the total order, which includes the order.
No, I just look at the quantity sigma over sigma 1.
Yeah.
If sigma 1 is very much bigger than sigma, then P star will be big. Bigger.
I mean, that also kind of.
Theta star will be smaller because it's reciprocal.
That also kind of makes sense because when you receive a large volume of buy order, then market maker will expect the actual V to be big as well.
So is there any interpretation related to for the insider? It will trade smaller when the market price is higher.
Insider. So here, insider does not trade based on the market price, right?
No,
insider only trade based on true value of V. Right, but the information structure here is that the insider only observe the value V is not affected by the market clearing price insider strategy. The market clearing price set after insider makes the order. So there is an order of actions here.
You are doing the stacker.
So far, it's a one-time step.
Yeah. So meaning that if the insider trade is small, then the market price will be higher.
Yeah, and no wait.
Because it's a reciprocal.
Yeah, when the insider trades small.
Sigma over sigma 1 is small, then P
Yeah, so
then the reciprocal will be bigger, right? Is there any reason for that?
oh wait, but if you so that's a linear function on theta. Yes, Q is linear on theta. Then if you plug this in, that just cancel the constant over the total order. No. So Q is what theta plus the noise trade, theta plus the noise trade. Here, theta plus the noise trade, and then you receive the total order. So then, yeah, if you plug that into Q, then that's really not affected by the total price is really just affected by V then, in that case.
Given the observation Q, that's what the market maker observed.
Yeah.
And given the value V, which is the insider's observation.
Yes.
And look at the quotient.
Yeah.
It's somehow it's reciprocal.
You got a 1/2 of
The
V all the
1/2 doesn't
time,
matter.
right? Plus no. You wait, when market maker actually set the price,
Okay,
they actually
okay.
just receive that amount plus a C and plug that in here, then that's always going to be 1/2 of V and then some noise trade.
You probably don't. Yeah, okay, just go on.
Okay. Yes, so now we can extend the model to continuous time. So the same method V. Now we model noise trader with Brownian motion, and insiders now have more information. Insider can not only depend on the true value of V, but also observe the entire order trajectory. So insider strategy also depend on Q, and Q now is defined as the integration over theta plus B, and market makers price also depend on the entire trajectory of Q. Insiders payoff are now just the same similar form, but in integration terms. So integration of theta times the difference between true value and the market clearing price. So here, in addition, we add a running cost, and well, it can be considered as a cost trading cost function, or the penalty function when considered when there is a legal risk present in the market that the insider trading can be caught. So, and we'll elaborate on that. Yeah, in the later part of the talk. Yes, so the insider problem is still the same. Given pricing rule, we'll try to find trying to maximize our profit. Market maker's problem is still also the same. Just given the insider strategy, trying to be close to the conditional expectation of V, given the trading trajectory Q. And the callback equilibrium is still defined the same. And then we'll introduce a classical solution for the callback model. So that's proposed by Beck himself back in 1992. But so the first two assumptions, that's for simplicity, but second assumption is kind of crucial. There's no trading costs in the model considered by Beck. And Beck proposed this solution. Callback is this equilibrium. So we'll analyze this a little bit more. So when insider uses strategy, one can observe that the trading volume process, order process become a Brownian bridge. So what does it mean? It basically have the same distribution as the Brownian motion conditioned on the terminal value to be that constant, which appears here. So another important property of this strategy is that it's not L2 integrable. And also observe that we'll plug this strategy, we'll plug that Q here at terminal time, it will just, the true value will naturally become V. Oh, sorry, the market clearing price will naturally converge to the true value V. So yes, so basically sigma cancel with the sigma mu plus V minus mu. And the Brownian bridge is a continuous process that smoothly goes to true value of V, which we find it questionable since when the insider information is revealed, there is usually a price change, either jump or hike or drop. Another feature is that, so even though the model setup will allow the insider strategy and the pricing rule can depend on entire trajectory of Q, then but this bridge solution only use Q at time t, so it's just Markovian. I guess one way to interpret it is that when the insider uses this strategy, the market maker can just set a pricing rule, make a guess to the conditional expectation of V without actually using the full trajectory of Q. So I think that's a bit unreasonable. And lastly, again, there are no uniqueness result when there is no restriction on the insider strategy as well.
So a quick comment.
Yes.
No uniqueness result is different from not unique.
That's true. Yeah.
We don't know it's unique.
Yes.
We don't know.
Yeah, that's true. Oh, yes. Okay. So literature review, more literature review. So the model was first proposed by Qiao in 1985. Qiao proposed a discrete time, the one-time step model we just discussed, and the discrete model. And then back extend the model to a stochastic differential setting and propose the bridge strategy we just discussed. And since then, more and more, there are many extensions proposing different features on the callback model, including Professor Ma and his student Tan did the dynamic insider information model. And also want to mention, so the F part, we got the idea of, so there are a string of literature on considering the legal risk, callback model under legal risk, which was mainly done by Umu Chatin, who gave a talk here last year. And that's also when I first learned about the callback model. So most of the literature mentioned here, trying to construct an equilibrium using a PD approach that requires some assumption, requires a certain Markovian structure for the pricing rule. And we want to get rid of this kind of assumptions. So which brings to our project. Well, our goal is to propose use a new approach to solve the callback equilibrium that is able to find non-Markovian equilibriums. And then we also want to use method. So the quotation mark on here is because it's a common method in stochastic optimal control games. And since there are, it's very hard to establish uniqueness results in the callback model, so we try to characterize all the callback equilibria instead. And we'll try to characterize the corresponding set value. All right, so the new approach we propose is the so-called Waker formulation from stochastic optimal control literature. So what do we do? So for each strategy function theta, we can define a martingale M. And we wanted the M to be L2, so that means additional assumptions on theta. So basically, we require to be L infinity to be bounded strategy sets. And with this, we can define stochastic process B theta and P theta using Gersanov. And B theta B is P theta B Brownian motion under this new probability measure. So, okay, recall how do we define Q as the sum of BT, the noise trade plus trade from the insider, the integral over theta. And if you compare these two structure, since B is a P Brownian motion and B theta is a P theta Brownian motion, then B under P theta B should have the same distribution as Q under P. So which can be used to rewrite our insider problems. So now so we change the expectation to the insider payoff into p theta probability measure, then suddenly theta and p become a function of
Can
b
you go
only.
back? What is Q?
Q is the total order, right? So the insider order plus the noise traders order. And that's the new process we just defined. So Q will correspond to this part. So they are parallel.
B is
So B, so since B is P Brownian motion, B theta is P theta Brownian motion, then B under P theta B must have the same distribution as Q
okay.
in terms of distribution. Only hold when we take expectation. Yeah. Expectation is enough because all the insider payoff are in terms of expectation. So we're allowed to pull off this trick. Now the theta and P suddenly becomes a function of B only.
You missed the minus F.
Oh, that's right. There is also a minus F here. Sorry. Yes. But the minus F doesn't, doesn't change.
Otherwise you may not be able to get
The
L2.
Hamiltonian, yeah.
Theta cannot be L2.
Yeah. Yes. So then we apply marginal representation theorem to get the BSDE under B theta V now, and then plug back in the definition for B theta V to get the BSDE under B.
Do you have any specific requirement for F?
For F, the requirements are all on the H. So when we actually do it, so F are good enough such that H are smooth. Hamiltonian is smooth.
Not necessarily convex.
We yeah, no, I don't think so. So we
Yeah, but
Yeah.
is capital H is convex?
we don't need
You
to.
have the transform.
Yeah, I already don't need it to be convex because using H, I already constructed optimal one. Because it's already taking soup here. So I guess for a good enough H, the F is better. F to be better to be convex. But we skip that discussion and just put the restriction on H. Yeah. Right, and then back to the BSDE here. So the BSDE at time 0 will give us a payoff when the insider using theta V. And then yes, we define the Hamiltonian, and the optimizer of the Hamiltonian is just H, the derivative itself. And using this Hamiltonian, we can apply the comparison principle of BSDE and just solve the optimization problem for the insider to using the BSDE generated by H. And the optimal strategy is also just H prime of the parts inside. Okay. So now we can also, the wave formulation can also help with the market makers problem. So basically we are able to rewrite the conditional expectation of V given Q under P is the same, has the same distribution of V given conditional expectation of V given B under P theta, which is the joint law. So basically means that VB under P theta has the same joint law as V and Q. And then we can apply the result from filtering literature, the Klemperer-Strobel filters, and find the explicit or somewhat explicit expression for the P. And so basically the P will satisfy when you put it under P theta V density, which V is given. Here V is the random variable V. then it will have the same expectation of P theta will plug in Q. And that's what we want to use for the insider problem. We also are able to say more when V is has a discrete support on V1 to Vn with the mass P1 to Pn. We can define a stochastic process X in this form such that the n-dimensional stochastic process X is exactly the conditional law of V given the Brownian motion under P theta measure. And the pricing rule will become the sum over Vi times Xi. So the basically now since V is discrete, the integration over mu will become the summation of times of these times P's. You just add them up, and that gives you the X. So now we have a SDE from market makers problem and a BSE from the insiders problem, and they're coupled by the fixed point. So they're coupled by the fixed point argument, so we'll get our FBSDE. And indeed, we're able to show that if this FBSDE has a strong solution, well, all the Kalbeck equilibrium can be characterized by a strong solution of the FBSDE. And the equilibrium will taking this form, P will be the sum of Vi times Xi. Theta will just take advantage of H prime, and we see happening coming from this part. I guess powerful questions. Okay, so yes, but FBSDE is really hard to solve. Indeed, Professor Ma dedicated a book to it, and we couldn't find a method that's really establish a good global well-postness result on this FBSDE. But at least when the time duration is small, then the problem is easier, and we can say that this FBSDE is indeed well-posed when the time duration is small, and thus the Kalbeck model is has a unique equilibrium. So, to the best of knowledge, this is the first uniqueness result when we do not impose too much restriction on theta on the insider strategy. And under this, the unique equilibrium that is solved, that we solved, the pricing rule is a function of the entire n-dimensional vector Xn random processes.
People might have a little bit of problem. This is when you say this is example, because your requirement that the theta is L2, probably a lot of people will, like the bridge case, they are not saying that.
Okay, there are two issues here. First of all,
so you can add F. When F equal to 0, then essentially they say this is
theta being L2 is not too much.
Not the Kalbeck problem that people originally
right, but
in the literature.
Yes, so there are two problems. First of all, when I say theta to be L2, it's not like it's more a technical condition instead of like a structural condition, which people typically use in this type to study the Kalbeck model. So I would say that's somewhat improvement. And then also the bridge strategy can be included in the set value, which we'll discuss later.
That's another thing. That's another thing.
Okay.
Because maybe this is a case when the Kalbeck problem in your case, in your sense, is unique when capital T is small.
Right, but besides changing the requiring theta to be L2 and the transaction, including the transaction costs, they are not. As I would say, we're solving the same Kalbeck problem than as the people usually does. So we didn't really change the problem at least importantly, the information structure of the problem. We did not change that. Yeah,
So when you say T is sufficiently small,
yes.
then how small is it and what does it depend on?
Then you can develop some estimate, like from the standard FBSDE theorem, or probably depend on the smoothness of H. Yeah.
Is it related to existence and uniqueness of solution to 4 or not?
It is. Just when T is sufficiently small such that this FBSDE is well posed, then the Kalbeck equilibrium is also has a unique equilibrium. So that is a characterization of all the Kalbeck equilibrium we can sort. Yeah. Okay. Right. So the pricing rule is a function of the entire random vector x. So it's which is significantly large. Dimension can be very large if the discrete value v has take many possible value. So I think it's very unlikely that it's Markovian. So which at least motivate us to explore the possibility that the Kalbeck model has many non-Markovian equilibriums. Yes. Okay. Next part, since the Kalbeck model typically does not have there's very little uniqueness results on the no uniqueness result on the Kalbeck equilibrium. So we'll try to characterize introduce a set value framework and characterize the set value characterize all the possible equilibrium of the Kalbeck model, or more specific, the value achieved inside the value achieved at the equilibrium.
Another comment. You suppose you have your equilibrium, you find your equilibrium for which theta is L2. Then you already showed Kyle's original work.
Mm-hmm.
The bridge case, it's not L2. So
yeah,
that's the evidence. It's if both are the equilibrium, then it's not unique, right? Because yours is L2, theirs is not.
That's
that one.
Yeah.
If it is also solve the same problem, that's the bridge that you have. It's not L2. That's like you said.
Right.
And
I would,
for some reason, you find the L2 solution.
Yeah.
So it's already evidence that unique. If you solve the same problem, the solution is not unique.
Okay, I guess that it's an issue of even if it's only if we only consider L2 solution.
Theorem, the Kyle's original solution is not the equilibrium.
In our
claim this in the conference. That's why
I'm not that brave.
Do you need help?
You probably alter the problem. That's
No.
then you know.
So Kyle's original, not Kyle, Beck's original example you showed in page 3 or somewhere does not satisfy our technical conditions. So that example in our result, there's no solution.
Yeah, you can see that because it said that you do not claim that you have to solve the same problem as they. But if you say that, a lot of people will jump up and.
Well, I'll defend. It's the same problem. I mean, it's a technical.
No, but you are claiming that all the bridge results are not the solution?
No. It's a technical.
It's not yours, it's the solution to your problem, but it's a solution to their problem. Isn't it?
I do think our solution is more reasonable. I don't.
No, don't
Okay.
just say that you are against the whole literature.
Right.
So you can say I add the F, I add the penalty, and whatever, but you cannot say their result, so many years, the results are not the solution.
Yeah, I guess there are difference
Because
between
you
the,
modify the problem so that you can have a unique solution. But their solution is not your solution. That's for sure. For their problem, no matter what, the T
Actually,
capital
we
T
think-
is small.
so at least
Their solution is not included in yours because it's not L2, no matter how small the T is.
That's true. If it's not L2, then but I mean without too much the technical assumption, but we're trying to check. But I think it's true that for example the bridge solutions from Umut's literature, I think somehow is a solution.
There is a book under that Markov bridge.
Yes. Yeah.
So the essence is that the bridge essence is not L2.
That's true. But
You find the uniqueness in the L2 class.
yes.
Therefore, the problem probably is altered from or modified or cannot be the same.
I guess
If you have a unique L2 solution, then their
I
solution
think
is
we
not
can we can argue.
So my
afterwards.
point is, don't claim too much. Otherwise, you know.
So I think the
there
message
is
is very clear. It's exactly the same concept, except the integrability requirement. Except the integrability.
Yes.
That's it.
I agree. Yes.
It's exactly the same problem, except we require the strategy to be reasonably integral.
Yes. Yeah. It's a matter of what do you think if the two problems has just two different admissible strategy set? Are they still the problem when everything else are the same? Right. Now yeah. So the set value approach. So we'll define the set value, but we do not define it as the value achieved at the set of the value achieved at equilibrium, but define in the limiting sense. What do we mean by limiting sense? So it's a set of the limit of the epsilon equilibrium when the limit exists. And what are the epsilon equilibrium? It's a strategy set theta epsilon p epsilon such that we're given p theta when insider uses strategy epsilon theta epsilon, the insider achieves epsilon optimal. And given theta epsilon, when market maker using p epsilon, then it's epsilon close to the conditional expectation of V given Q. And when we plug those epsilon equilibrium into insider's payoff and taking limit as epsilon goes to 0, if those if the limit exists, then it is part of the set value of the Kabak model. So why do I define the set value in this way? One reason is that recall that the insider's problem is defined exactly as a soup problem. So by nature is defined in the limiting way. The equilibrium is defined in the limiting way, and the optimal control problem, in the optimal control problem, the optimal control might not exist, but the optimal value still exists. And case in point is when Professor Ma mentioned that within our restriction on the theta, then the optimal control doesn't exist. But by taking some truncation of the bridge solution, then we can recover the bridge solution by taking the limit when epsilon goes to 0. So next goal is to characterize the set value. So basically we do this by just solve an optimal control problem. So one of the difficulty was that to solve the FBSDE. So in this approach, we want to just treat this BSD as a forward equation and pick the Z part as the control. And we want to define the cost as the difference between this forward Y and the original backward Y at terminal time. And also the theta chosen by X insider. So here, this part controls the difference between the control theta and the actual optimal Hamiltonian value. when the cost is 0, and we call the initial value for y as the level set of the control problem. And so yes, when this cost is 0 for the given initial time t and t0 and prior distribution p, the y that this w achieves 0 is the level set, and we show that this level set coincides with the set value of the callback model. And with the optimal control problem, we can use all the tools in the optimal control literature. For example, you can solve an AJB equation, and it's probably hard to get explicit solution, but I think there are numerical methods to treat this type of problems. And lastly, I guess I'll just go over this, skip this part. Basically, we're able to find a weaker form of the FBSDE when the weak solution of this FBSDE with additional martingale term that is orthogonal to B, when they have a weak solution, then the y0 also contained in the set value of the callback model. So lastly is I'll discuss a more practical problem, like more of economic stories. So the stealth trading is in this stealth trading phenomena occurs when there's an active prosecutor trying to catch the insider, but there are also a large group of noise trade happening, so that the insider can trade at the right amount of skill, right amount, so that it avoids the risk of being caught while still making some money, optimizing their profit. So yes, so the V is the same information structure for the insider and market maker stays the same, but now we have n number of noise trader ID burn emotions. Collectively, they behave like root n of B. So that's our new order process, and now there is a regulator also present in the market, and that is dynamically prosecuting the insider. So how do we model the prosecution process? Is through this calc process G lambda. So what does it mean? At time t, G lambda t behave like a Poisson process with Poisson parameter capital lambda t, and is determined by the entire trajectory of theta through integrating over a function on theta from the initial time to the current time. The feature of this theta is that so when it's smaller than there, so when the trade is smaller than 0, it's decreasing. When the trade is larger than 0, it's increasing, and when trade is 0, it's the lambda is 0, because, well, if insider makes no trade, then it shouldn't be caught. So this beta here, or n to the negative beta, basically model the prosecution intensity. So think.
What's that notation? Lambda 0, 1?
Oh, so the derivative on this part. So derivative larger than 0 means it's increasing. That's
what?
Derivative on the theta. So no derivative on t. First order derivative on theta.
Okay.
Yeah,
I would prefer write a partial theta lambda.
Yeah, I. That's one option. Yes. Yeah. So see, for example, when the beta is large, then n to the negative beta times theta is very small. So the whole value is near 0. The lambda is near 0. So the insider is unlikely to get caught. So basically, beta is inversely related to the prosecution intensity. So if beta is 0, then the prosecution intensity does not depend on the change of the total number of noise trader. Then, well, that's a consequence that we'll show later. And also, another feature is that the
beta is 0, then lambda depend completely on theta, right?
Yes, yes. So no matter how many noise trader there are, Inside trader will be caught, will have a probability to being caught. Yeah. Yes, so another feature is that the trade stop when insider is caught. So it stop at when the G lambda happens. Yes, greater than 1 for the first time. And after getting caught, there will be penalties. So there are 3 parts. First, all the profit of insider will be taken away. And then there will be criminal charge that depend on the strategies and civil charge that depend on the profits. So then now the insider payoff looks like this, but that's we can still handle it by the weak formulation and then using the BSDE. And then to optimize this y as a function of theta, so the Hamiltonian approach doesn't work because the penalty actually depends on the trajectory of theta. So you cannot find a optimizer for the find the optimizing theta path that maximize this generator of the BSDE, and that is actually optimizer for all t. So we nevertheless we just handle it by stochastic.
So y is supposed to depend on n in this case, yeah?
Where is that? Yes.
Yeah. So implicitly depend on.
I should have added an in the entire process.
So when n goes to infinity, you have a limiting problem?
Yes, that will be
Go.
Yes.
Limiting is interesting, yeah.
Okay. So yeah, first observe that. So the Radon-Nikodym derivative will go to 1, the M process we define. So the price impact, so the price process will just become EV, will become deterministic. So meaning that as population increase, the price impact of insider trading vanishes. And the limiting problem will be just the insider's optimal control problem. So how do I define the insider limiting model though? So first define the gamma as a stealth index. And so now the theta tilde is the relative amount of insider trade. So when you multiply by n gamma, it's the actual amount of insider trading depend on the population, n. And then, so since n will go to infinity to avoid to keep track of the model, we also just divide the profit by n gamma. And the optimal gamma limiting optimal strategy theta tilde is when this J tilde achieves soup, but not using a zero or is not using a zero strategy or reaches its upper bound. When it's 0 means that the trading skill of the insider relative to population should be relatively smaller than n gamma. So then just we should consider smaller model with smaller gamma. When on the opposite, when it's when insider is need to trade at as much as possible, meaning that gamma is too small, and then should adjust accordingly. So then also the insider utility becomes this form. So what's important here is that since price is now deterministic, all the noise are coming from for the insider are coming from the price. So now insider just don't need to choose a random strategy, and the problem becomes deterministic optimization problem. And there are like more tools in the optimal control series for that. So lastly, a bit more economical message. When we pick a more specific penalty form. So the criminal charge will be the LP norm of the theta to the power of alpha. Basically, it will penalize a lot when you have a very volatile trading pattern instead of a very flat trading pattern. And the last part is the civil charges is just a constant multiple of the profit. And furthermore, just to keep track of the prosecution intensity when theta is around 0, we say its order is eta. then we are able to, we show that there exists a unique gamma limiting set optimal strategy for gamma to be taken this form. So what does it mean? So as I point out, so when beta is 0, no matter how large is the noise trader, the insider strategy will affect his chance on getting caught. So insider strategy also shouldn't change with population. So gamma should be 0. And when this part is, when alpha is 1, so this part is less significant, the insider can trade at a rate of beta. And when this part is more than 1, the gamma insider should trade as a even lower intensity than beta. So for in the future also, so the future project, so for future work, first we want to study the dynamic of the insider values, because the insider's profit kind of depend on the conditional law of a conditional law of phi given the Q filtration. So can we study like using a mean field game approach? That's the direction we want to explore, and also want to extend the model to a continuous prior distribution V, which I think could lead to a infinite dimensional system. And nevertheless, we'll try to approach it. And for the stealth trading part, we want to study how the strategy change as p goes to infinity. So as p goes to infinity, it will be the penalty will depend on the maximum of theta trade. So how does that?
What's P? Sorry, I forgot.
Sorry, the p norm. So this part. So the criminal charges, which is the p norm of the insider strategy. So in this part, p and eta doesn't show up in this analysis. It will affect the exact strategy used by the inside trader. So, but it's interesting to like see qualitative analysis. How does eta and p affect? And lastly, we also want to kind of study the regulator problem, kind of related to the noise traders objective kind of question. So how to in the Umu's paper, the objective of a regulator is to minimize the loss of noise trader. But I think that is not our case in the model, especially when n goes to infinity, as insider has very little price impact. So what should be a reasonable regulator's problem? I don't know, maybe, yeah, or to be explored. So that's it. Thank you for that.
We cannot see that again, or
I don't know.
the time is set.